Welcome back. I hope you're having a great time at PyLadies Con 2025 with us. I'm super excited to introduce our next speaker, Lilinoe, who will be talking about MLOps for MedTech. Her session title, Trust Me, I'm a Robot, MLOps for MedTech. Give a huge round of applause for Lilinoe. The stage is yours.
My name is Lilinoe Harbottle, and this is Trust Me, I'm a Robot. MLOps for MedTech. A frozen app on your phone can be annoying. But what if that progress bar belonged to a robotic surgery system? What if it was during a robotic surgery for a cancer biopsy, where a stall could mean the difference between success and failure? That catastrophic risk is the problem we'll discuss. The global market for medical robotic systems is growing. It's projected to reach about 75 billion US dollars by the year 2032, growing at 17% compound annual growth rate. This massive investment is subject to risk. The average cost of system downtime for a critical service is over 2.1 million US dollars per incident. This risk is universal. Recently, in the news, a major financial institution's AI algorithm used for mortgage approvals was found to exhibit systemic opaque bias, costing the bank millions in fines and reputational damage. We're engineering guardrails. Trust in AI-assisted surgery breaks down into 4 layers. Logic. Is the prediction sound? Competence. Will the system survive failure? Human agency. Does the surgeon retain control? Security. Is the data safe? The MLOps pipeline looks at these 4 areas. In the healthcare domain of minimally invasive surgery, the robot is a surgical console system. The surgeon controls the robotic arm. The data proves its necessity. Traditional bronchoscopy reaches only 23% of hard-to-access tumors. Robotic systems boost that diagnostic yield to over 84%. This precision enables efficiency, cutting time from biopsy to treatment to just 28 days, half the national average. Yet without an MLOps blueprint, this complex model is a liability. According to research, about 87% of deployed ML models fail, and it's a universal problem. This failure rate could apply to your critical system in logistics or finance. So the approach to solve this would be reliability. And to frame MLOps in the larger scheme of AI, it's a small critical corner automating the validation, deployment, and correction phases. So we're building the scaffolding for all other AI initiatives to stand on. This MLOps layer is what separates a proof of concept from a life-critical deployment. So this demo needed a managed MLOps platform for governance and auditability. I used GCP for this demo, but the principles are platform agnostic. Think AWS SageMaker or Azure Machine Learning for parallels. Solving failure in minimally invasive surgeries demands the highest engineering standard. The core purpose of the blueprint is reproducibility, traceability, and controlled deployment. This governance layer is non-negotiable in healthcare, but it's also essential in other high-stakes systems. This particular project relied on Python for 3 key layers. Apache Beam for scalable stream processing. TensorFlow Lite for low-level edge performance. And the rich ecosystem that makes industrial-grade reliability accessible. Python is the universal language of MLOps, handling both the cloud scale and the device edge. One of the first concerns is preventing downtime. The robot's telemetry, aka its heartbeat, is sent via scripts to a decoupling layer, like PubSub. AWS, it would be simple queue service and simple notification service. In Azure, Event Hub. This architectural pattern of decoupling is critical. For example, consider fleet logistics. If a connected semi-truck loses cell service, the telemetry data must be collected and queued locally. This architectural design provides resilience and fault tolerance. So we used Apache Beam running on Dataflow. A parallel would be AWS Elastic MapReduce and Azure Stream Analytics. And why Apache Beam? Beam was essential because it handles the Lambda architecture principles of unified continuous streaming of telemetry and batch analysis of historical logs. This consistency is core to level 2 MLOps maturity. The Python logic flags an anomaly if a vibration is greater than a certain threshold. For example, in a high-traffic SaaS application, this same pipeline could detect resource exhaustion or anomalous user behavior that threatens service stability. So to recap, the pipeline enriches the raw sensor data. It aggregates the anomalies and writes the structured output to our data store. This architecture turns raw data into data for governance and quantifiable action. This detection is a commitment to responsibility. Another approach is a managed alerting service, for example, cloud monitoring, which would target the aggregated anomaly count. This triggers a serverless compute function, which is a quantifiable way to take immediate action to mitigate risk. This pattern could directly transfer to other areas, for example, in fintech, detecting real-time fraud based on anomalous transaction velocity, or in ad tech, stopping a campaign immediately if bot traffic is detected. So the blueprint ensures that the loop is closed. Data drift is the silent failure, and this issue is complicated by data diversity. Due to strict regulatory constraints like HIPAA and GDPR, MedTech may work with anonymized, siloed datasets. This is a cross-silo challenge that many enterprises face. Let's look at the cybersecurity context. In 2024, healthcare was the 5th most targeted industry for cyber attacks, often exploiting weak identity controls that comprise data repositories. The principled approach is to audit the model's behavior, not just the raw data. So we would use a managed feature monitoring service. So this model computes the feature distribution skew, a core statistical output between live data and the training baseline. In ad tech, the skew could be a new browser privacy setting or a sudden market shift that invalidates your targeting model. The skew could be measured and quantified in multiple ways. The core defense is testing with concept activation vectors, and this provides explainable AI principles, statistically auditing if the model relies on spurious correlations. What this does is it ensures the model is not just relying on certain protected attributes. Additionally, before deploying, you would also validate against a digital twin, a simulation, to ensure that the model is robust to unseen variations and moves beyond basic unit tests. Another challenge is latency. You can imagine that for imaging and modeling, the high volumes of image processing is resource heavy, but brief lags could break the immersion and a surgeon's flow. How do you promote efficiency and independence to ensure timely results? A Python solution in this case is model optimization using post-training quantization. This is not just a compression, it's an efficiency transformation. What it does is it preserves human agency and reciprocity so that the surgeon still controls the end effector, not the clock, by maintaining a near real-time fluid experience. Taking it further, the performance data would feed into the model registry, such as Vertex AI in GCP, SageMaker in AWS, or Azure ML, which serves as the technical audit trail. The audited metrics would guarantee that the human operator retains autonomy to make the final deployment choice. This is the reliability that the system could offer. The path forward involves continuous improvement in safety and in alignment. But these universal principles, decoupling, integrity checks, efficiency, could be applied across many industries. So to recap, we had built a reliable system by focusing on core values of trust, responsibility, and integrity. I invite you to explore this code base.
Wow, that was an incredibly informative session. Thank you, Lilinoe. Well, 87% of the ML models fail in the larger production circumstance, and AI getting into these critical industries, we definitely have a solid understanding of what could be done and what needs to be done. Thank you so much. Well, stay tuned. We have a lot more exciting sessions coming up for you.